Okay, students, good morning. Uh, we give another 2 minutes for your friends. I think only 3 of you here. Good 10 of you here. Change project. I mean, give me check my one.
Yeah.
Okay, let me take your attendance. Okay, I think all 12 of you here. Okay, good. Okay, class. So let's start with a new topic here today. Later, I have some questions for you. Work energy power. Some question asked by your friend. We'll discuss that. But before, we start with the new topic first. Okay, so this is actually not topic 9. It should be topic 7. Okay, so I need to change that. Topic 7. Okay, so AS, you got how many topics? Yes, you have 13 topics. So 13 topics. I think before your semester exam, which is going to be scheduled in the end of June, 22nd, I think, your June, you have about 3 weeks to go. So we'll be finishing, the exam is up to topic 10. Okay, so we'll be finishing up to topic 10 before your semester exam. Okay. Okay. So this is the 7th topic. It's about deformation of solid. Okay. What is meant by deformation of solid? Like your Hooke's law last time. You hang a wire, you add the load until it breaks. So how the graph looks like. So that's what we're going to investigate here. Okay. Last time you take a spring, you add a load until it go up to elastic limit. You never go beyond elastic limit. But in this topic, we're going to go beyond elastic limit, and we're going to see until it breaks. And we're going to find the graph force versus extension. Then we're going to group them in a particular different type of material. For example, like ductile material, brittle material, and rubber. Okay, so that's our discussion under this topic, deformation of solid. Solid deforms until breaking. Okay, how is it behaves? Okay, so these are the outcomes. I don't want to go through this. You can read this. First thing. So what is solid have the ability to retain its shape after the force is removed. Okay, it's rigid. Solid do deform when a force is applied, but the deformation is too small. Too small. You can't really see it. Rubber deformation is quite good, but rubber also solid one. But like metal, the deformation is quite small. Okay, so you can break the material in 3 ways. These are the 3 types of stress we can apply to the material. It's called tensile stress. Tensile, we try to apply force away. So tensile stress. This is compressive stress. You compress them. Compressive stress. And this is called shear stress. Shear stress means sideways. Sideways. So you're going to extend sideways. Okay, shear stress. We are more focused to tensile stress. Okay, tensile stress in our discussion. Okay, so how you can deform a material by applying stress, or in other words, applying force. Tensile, and we go more to stress tensile stress, compressive stress, shear stress. Okay. Okay, for example, you see this computer table here. So in A level, they will ask you to identify, is it the rod is under compression or tension? Okay. For example, you see the computer on top here, the computer about to fall down. This rod is under tension. Okay, it's under tension because imagine like you are taking a knife, a saw. Let's say you cut this piece, put a small crack here. What will happen to this bar, this rod? It try to go apart or going to like collapse? Like it will try to go apart, right? Okay, when you like cutting here on top, so it try to go apart. If it try to go apart, then we say it's under tension. So A is under tension. Okay. B, the bottom here, you see the bottom bar here, this bottom bar is under compression. Okay, it's under compression. Let's say you make a small cut here. What happened? The bar will collapse. Will collapse means start to stick together. They won't move apart. If they collapse, we say it's under compression. So B is under compression. Okay, look at the C one. So B is under compression. It's under compression. Look at the C and D. C, this part, C. Let's say this rod want to go bend to the left. The D region, the outer region will be under tension. The C region will be under compression. Okay, so it will be under compression. Okay, so you need to identify, is it under compression or tension? Okay. So look at the bridge here. The bridge here, the car, when the car passed by, the bottom is under tension. The top is under compression. The top is under compression. Here tension. Let's say you make a crack here. What happened? The crack going to make the thing apart. It's going to split. Try to split. So it's under tension. If you make a cut on top here, it's going to collapse. It's going to connect together. They won't go away. So then they under compression. Okay. So as seen in the example, when the force is removed, the object tends to return to its original shape. Okay. What is the thing that has similar effect is the elasticity. Okay, so solid are like spring. It's like spring. When you give a force applied, it will extend. When you let it go back to the original length. Okay, but the extension is not that big. That's the only thing you can't see. It acts like a spring. The solid exhibit elastic behavior. Okay, it exhibits elastic behavior. What is meant by elastic behavior? Anyone? What is meant by elastic behavior? The ability to get back to original length after the force is removed is called elastic behavior. Okay, the ability for an object to get back to original length after the force is removed. So all the solid experience elastic behavior. Okay, all metals and everything. Okay, so now let's recall behavior of spring. Our first lesson today is more to spring. Okay, Hooke's law. So spring here, you can compress it, you can stretch it by applying a force. So of course, spring means Hooke's law. 2 marks Hooke's law. What Hooke's law stated? The force applied is directly proportional to the extension of the spring, as long as what? Say F equals to kx law, Hooke's law. The k is spring constant. If you plot force versus extension graph, the gradient is your spring constant. You learned this before. The elastic potential energy, the area under graph is elastic potential energy. Of course, half fx, or we can say half kx squared. Elastic potential energy is taught. I think these two you already learned before. Okay, spring constant. Let's say you have two spring. Your mechanical pencil inside got one small spring. Your car suspension system, there is a spring at the wheel, huge spring. Okay, which spring has a greater spring constant? The one in the mechanical pencil spring or the one in the car? Which has a greater spring constant? Greater spring constant means the spring is difficult to extend or easy to extend? Big spring constant. Should be difficult to extend. Bigger the spring constant, difficult to extend. So which one has a higher spring constant? The car suspension spring, that spring has a higher spring constant. So greater gradient F versus X graph. Okay, so E of kx squared. Okay, so one easy example. A spring 0.5 meter long stretches 0.58 meter when a 5 Newton mass is hung vertically. What is the spring constant? So 5 Newton is the force. Extension is how much? 0.08 lah. 0.5 the original length stretched to 0.58. So F equals to kx. So 5 divided by 0.08 give you the spring constant 62.5 Newton per meter. So unit for spring constant is Newton per meter. Okay. So greater the spring constant, more stiffer the spring. We call it. Spring constant measures stiffness of spring. Put in your mind. Measures stiffness of spring. Then find the energy that is stored. Half kx squared will lead you the energy 0.2 joule of energy stored. K is 62.5, x is 0.08 squared, so you get the answer. Okay, this is something new, if I'm not mistaken. I don't know whether you learn in your O levels or SPM or not. We're going to have spring constant in combination. We're going to connect them. This is one single spring hanging a mass M. K, let's say the spring constant is K. Let's say the spring connected like this in parallel. What happened to the spring constant of this system will be? Rises or decreases?
Increases.
Yeah, rises. Increasing. It increases. It gets more stiffer. You put more spring in parallel, very difficult for you to extend. So what is the new K value for this spring? So if the only one spring is K, means two spring together is 2K. Okay, so it's 2K. So this is connecting spring in parallel or series. This is connecting spring in parallel. Okay, if connecting spring in parallel, that means the K total should be the K1 plus K2. This is the formula. Let's say this spring has a K1, this spring has K2. So the K total is K1 plus K2, the new K. Okay. So 2 times more stiffer than the original spring. If you connect in series, it's going to be less stiff than the original one, right? Easy to extend one. This one is easy to extend. So what is the new K value for this series? Will be K over 2. Okay, this one will be K over 2. So how the formula for K for this series spring will be? 1 over K total equals to 1 over K1 plus 1 over K2. Yeah, this is the formula to find K for spring in series. You just 1 over K, like last time your circuit resistance in parallel, how do you say? 1 over R total equals to 1 over R1 plus 1 over R2. Same thing for K here. K here, spring connected in series will be 1 over K total equals to 1 over K1 plus 1 over K2. Okay, so eventually you should understand that if you want to make the spring less stiff, connect them in series. You're going to extend a lot. If you want it more stiffer, then you have to put them parallel. If get more stiffer means the K get bigger. Okay. Okay, so F1 plus F2, this derivation of it. So the final K is K1 plus K2. The derivation you don't need to know. Okay, but you need to accept the final formula. The K, just add them. Okay, 2K for this case. And for series, the x1 plus 2, the formula is 1 over K equals to 1 over K1 plus 1 over K2. We just accept the last two. The derivations no need to know. Okay, so it's become half K, less stiff. Okay. Okay, one exercise for you. Okay, you have two springs, two different springs. A and B, A as a spring constant of 8, B as a spring constant of 2. The question is, load 10 Newton is applied at the bottom. Okay, find the extension in each spring. How much the extension of each spring will be? So the load is how much? The load is 10 Newton. The load is 10 Newton. So the A is 8, and force is 10. What is the extension of A will be? Extension of A equals to the force experienced by A divided by the spring constant of A, all A, right? The force experienced by A. What is the force experienced by A? What is the force experienced by A? Exactly 10 Newton. The A and B, do they help each other to carry this 10 Newton? Do they help each other to carry the 10 Newton? Not really. They're not helping each other to carry the 10 Newton. They are like individually carrying the 10 Newton. For, let's say, for the case of A, B is like a burden for him. B does not help him to carry the 10 Newton. So the force experienced by A, the force is exactly 10 Newton. The A experienced 10 Newton. Divided by the K of A is 8. So that's the extension experienced by the A. Okay, 10 divided by 8. Okay, so that's the extension for A. The extension of B will be what? Extension of B will be what? Again, force experienced by B. So the force experienced by B is also 10 Newton, but the K is 2. So the extension of B will be 5 centimeter. It's 5 centimeter. 10 divided by 8, how much you get? 1.25. 1.25, yeah. So get 1.25. You get 1.25 centimeter. So find the extension of each spring. One is 5 centimeter, another one is 1.25 centimeter. Okay. So yeah, 1.25 and 5 centimeter you should get. Okay. Then the spring constant of the combination. What is the spring constant of this combination? 2 ways to do. Okay, the new K you can find. Of course, earlier we found that is K1 plus K2 is your total K. So in this case, sorry, this series, right? Series means 1 over K lah. 1 over K, 1 over K1 plus 1 over K2. So you put your K1 and K2, that means 1 over 8 plus what? 1 over 2. You get the 1 over K total. So your reciprocal, you should get 1.6. This is one way of finding. Another way of finding is using this total extension. So what is the new K? The force over extension. Okay. The force applied is 10 Newton. The extension is the total extension. What is the total extension here? Here is 1.25. Here 5. So total extension is 6.25. 6.25. So 10 divided by 6.25, you'll get the same answer. So 2 ways of finding the K. 1 over K1, 1 over K2, you can use it, or you can take force divided by the total extension. Okay. So this is the first warm-up question. Okay. 2 in series. The force experienced by A and B will be the same. They are not helping each other. Whatever load applied here is the force experienced by A. Whatever load applied here is the force experienced by B. Okay. Any questions so far? Okay. So let's go to the next one. I clear this. Okay, next one. Next one, the A and B is in parallel, placed in parallel till the 8 and 2 is applied. Ka is 8, Kb is 2. Okay. Now the springs are parallel. A load 10 Newton is applied. If extensions are equal, how you make it equal? Oh, you tell me here. How do you make the extension of A and B equal? By putting the load more closer to B or more closer to A? How do you make the extension equal? By applying the load more closer to B or more closer to A?
Oh.
Yeah, anyone? More closer to B or more closer to A? You get the same extension in parallel.
More closer to A.
Yeah, very good. More closer to A. So you put more force to a stiff spring so that the extension is the same. In this diagram, I think the load must be quite close to A to have a same extension. Okay, so let's get back to the question. Now the spring are parallel, 10 Newton. If the extension are equal, first question, find the spring constant of the combination. Okay, so what is the spring constant of the combination? The extension of the spring. So how do you find the spring constant of the combination? The K1 plus K2. The spring constant is just 8 plus 2. That's the spring constant lah. The 2 K1, K2 add up, you get the total K. Okay. Then what is the extension of the combination? The extension of the combination, of course, x equals to f equals to kx. So find the x lah. Find the x. So x is 10 Newton divided by x divided by what? Divided by, sorry, yeah, k. K is 10. So you get 1 centimeter is that time. Okay. So series parallel. Okay. Okay. So your these are questions. I don't want to do this. Sorry. Let me. I straight go to this question. I think this is quite easy. You can do. Go to this. Okay. Come on. First, 1 minute for you. What's the answer for this question? What is the order of increasing extension for this arrangement? Smallest extension to the largest extension. Okay. Okay. Let me get a number. Let me tell you one thing. Let's say this one spring. I just take one spring and I put a load. The load. Yeah, the load. Let's say the extension it experienced is x. The extension was found to be x. So can you give me the answer? This will be how many x? This will be how many x? This will be how many x? The first one, extension going to be how many x? One spring with a load, x. Two spring parallel with a load will be how many x? How many x? You're going to have more than x or less than x? Is it going to extend more or extend less than x?
Less than
So how many x?
half.
Yes, good. X over 2. So this will be x over 2. Okay, good. Now come to this picture. Same load, two platform. Okay. They are not helping each other. They are not actually helping each other. Like this two spring, just carrying the load, straight away load, like this two spring. So what is the extension here will be alone? These two spring sharing the load. So it will be x over 2. This also will be another x over 2. Like two people sharing the load. So the x divided by 2 lah. Here x over 2, here x over 2. So total here will be extension is x. It will be x. The extension, the second one is greater than the first one, of course. The third one, what is the total extension? They are not sharing. Up and down never share the load. They never help each other. So the first one, these two are help each other, the parallel. So here extension will be x over 2. This spring, this lone ranger, the one spring with the load, it is going to extend x. So total here going to be 3x over 2. So of course, so which is the smallest to largest? Of course, x, y, z. So the answer is going to be a extension. Okay, it's an extension. So this is how do you calculate the extension? Okay, let me ask you more questions from here. Let me. Okay. this. Let me clear this. Sorry. Okay. So everyone, try to do this question for me. You have one spring. You can see the whiteboard, right? You have one spring. We put 1 kilogram here. We put 1 kilogram of mass. The extension is found to be 1 cm. The extension is 1 cm. Okay, so this is the system. Okay, tell me what is the extension for this system? You have one spring. You have two spring. You have four spring. And apply 5 kilogram. 5 kilogram. Come on. Tell me what is the extension here? What is the extension here? What is the extension here? Therefore, what is the total extension? So one spring, two spring, four spring, 5 kilogram, not 1 kilogram. Here the picture is 1 kilogram. 1 kilogram extension is 1 cm. Now this arrangement placed with 5 kilogram. So what is the extension for every spring will be? The first one will be how much? This is a three platform. Three platform. 1, 2, 3. They never help each other. They never help each other. But one like carrying the 5 kilogram alone. The one platform, the first one, you can imagine like one spring carrying 5 kilogram. So what is the extension will be for the one? 1 kilogram extend 1 centimeter. 5 kilogram less than how many centimeter? Anyone? It will be 5 cm. Will be 5 cm. Will be 5 cm. Correct. So one going to extend by 5 cm. The first platform 5 cm. Because one spring carrying a 5 kilogram. 1 kilogram 1 cm. 5 kilogram should be 5 cm by assuming one assumption is what? It obeys Hooke's law. We assume it obeys Hooke's law. Okay, the first one is 5 cm. Second one, please, anybody can give me the answer. What is the extension for the second one? 2 spring carries 5 kg.
5/2.
Yes, good. 5/2. So 2.5 cm. Quite easy. So 2 spring sharing the 5 kg. 5 kg means 5 cm. 2 spring means 5 centimeter divided by 2. The third one, 4 spring sharing the 5 kg. So 5 centimeter divided by 4. So you get what? 1.25. The third extension. So altogether, how much? It's about 8.75 centimeter. 8.75 centimeter. Okay, good. So this is how you calculate. 1 kilogram is 1 cm. If the mass is changed, 5 kilogram, you need to find for one single spring, 5 kilogram, how many centimeter first. Then every platform, you have to calculate the extension, then add them. Okay, now, what is the spring constant for this system? So K equals to F over X. F is what? 5 times 9.81 divided by the total extension, which is 8.75. 8.75 will give the spring constant of this new arrangement. Okay. So one example of the system in series parallel combination. Okay, this one. Any questions from here? Hope you can understand. I think early studies you have learned this before. Okay, so let's see Cambridge questions about this combination. Okay, so let me close this. Okay, go back to this question. Okay, so before I go to this, I go to the question first. Okay, the question is question paper. Okay. Okay. Let me show you one question. This one. This is how Cambridge asks questions. 1 minute for you. This is page 3. Page 3, question 22. 1 minute for you. As usual, get me the answer. Send me answer through WhatsApp. Hope everyone give me the correct answer. 1 minute for you, eh? So beam of weight of neglected mass. Okay. 3 springs are connected in parallel. The weight is W, and the extension found to be X. W with 3 springs, extension is X. Now the middle spring and the weight are removed. Or the middle spring and the weight has been removed. What is the new extension? When 2W is hung from the middle of the beam. So finally, the final system got how many spring? The spring, 3 spring become 2 spring now, and the load is 2W. 2 spring, 2W. What is the new extension? 1 minute for you. Come on, give me the answers. Put it in WhatsApp. So far, I never get any answer yet. Give a try first. Okay, let me. Maybe I put it here. Eh? Maybe I can put the whiteboard. Sorry. Okay. Okay, let it open up. You can see the question. Yeah. Okay, so they're asking only 2 spring. Only got 2 spring with 2W. 2W. Okay. They're asking what is the extension? What is the extension? How many X? Okay, so I receive answer. Okay, I got one answer. D. 3X. Is it 3X? The others got 3X. So how to do this question? 2 spring with 2W. The original one is 3 spring. Original one is 3 spring with W. 3 spring with W is how much? 3 spring with W. The extension is X. Okay, you see, I draw a line here. I want to reach this system. First, what I do, I go for a single spring first. Single spring with W should be how many X? 3 spring with W, X. Single spring with W, how many X? Anyone? 3 spring with W is X. 1 spring with W, how many X? Should be more, right? Should be 3X. Yeah, right. Because 3 people are sharing the weight, X. So 1 spring yang is going to be 3X. Now let me go up. Yeah. Go up means now I want to change the load to 2W, but still 1 spring. 1 spring with 2W should be how many X? W is 3X. 2W should be 6X. Good, correct. 6X. So now you can go to this diagram now. So 2W, 6X. 1 spring, 2W, 6X. 2 spring, 2 spring, 2W. They share, right? Yes. So 6X divided by 2 lah. So should 6X divided by 2 lah is the extension. So it will be 3X. Good. Yeah. So those who got D is good. So the answer should be D. So my advice is they will give a system, then they'll ask for the new system. The load might be changed. The spring also will be changed. But you go back to 1 single spring, check how much is the extension. Then change the load to the new load, get what is the extension for 1 single spring first. Then you can do the combination easily. Okay, remember, for spring combination, always go 1 single spring with the load, how much first, the extension. Then you can solve any type of combination. Okay, any questions so far? So no question. I hope you understand. Okay, more questions? Okay. So let me questions? Oh, this one we done. Just another one. Let me see another one combination. Solar spring. Okay. Sorry. This one. This we did earlier. 20. What is the answer? This question, page 19. Page 19, question 20. Okay. This is the earlier one we did. What's the answer? So which part of the body is under extension? Which part of the body is under compression? A load is applied at the edge, L-shaped structure. Okay, I receive answer. It's B. Is it B? X is under tension. Y is under, X is under tension. Y is under tension. Yeah, good. Z is under compression. Okay, so the answer should be B. B. Do you agree, everyone? It should be B. How to know this? You just imagine like you are take a knife or a saw, let's say you cut here. Let's say imagine like you are making a crack here. Cut here. Okay. So like for example, okay, the structure is like this. Okay. So you apply a load here. You imagine like you're making a crack here and you're making a cut here. When you cut, what happened to this part? Is it going to move away? You're going to move away, you're going to collapse. You're going to try to close the cut. You'll try to move away, because you're going to like collapse like this. So if it's move away, this structure is under tension. It's under tension. Okay. So X is under tension, of course. Do the same thing. Y, you try to make a crack here. What happened to the Y? This part will move away. Okay. So this also under tension. Z, if you make a crack at the bottom, they try to close up. They will try to close up. So Z under compression. So answer is, of course, B is answer. B is answer. Okay. So I think another one. Let me see. Is there any spring questions arrangement? Yeah. Yeah, this one. The last one. Before you continue. 21. What's the answer? So assume one spring with load X. Tell me how many X for A, B, C, D. So which will have the greatest extension? So what's the answer? Greatest extension. Tell me answer. Okay, C. So yeah, if you say C, so of course, yeah, C is the good answer. C is the answer. Okay, so as usual, put here. This is annoying. Okay, so of course, one spring, we take it as X. So for the answer A, two spring in parallel with the load, of course, it should be X over 2. They share, so extension is lower. For the case of B, will be up X over 2, down also another X over 2. So all make up to X. Then the C will be up 2 in parallel, so it's X over 2. Down is only one single spring, will be X. So total is 3X over 2, the extension. And D is what? Up got 3. So So the x divided by 3, so the extension x over 3, and the down is only one spring, so it's x. So all together is 1.33 maybe, 1.33x. So the greatest extension is the C, 1.5x. Okay, so this is how series parallel works. Okay, so let's move on. Okay. Okay, so elastic behavior and Hooke's law. A material exhibits elastic behavior if the deformation produced caused by the force totally disappears after removal of force. So elastic behavior means ability to get back to the original, return to the original shape after the force is removed. That's the keyword. What is elasticity means? The ability to return back to the original shape after the force is removed. Okay, 2 marks question. Okay, what Hooke's law? I already told you. Hooke's law is extension of the material proportional to the applied force provided elastic limit is not exceeded. Okay, class, there is a mistake here. You can't use the word elastic limit anymore. O-level SPM used elastic limit, but it's wrong. It's not an elastic limit. There is another exact point we call limit of proportionality. Limit of proportionality. Let me show you the. Okay, where's the limit of proportionality? Let me see. Sorry. Okay, so the elastic limit, you have to change to limit of proportionality. So this is can't be elastic limit. You can't write elastic limit anymore. Must it limit of proportionality. 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 Okay, so that's the new term we're going to use, limit of proportionality. Those, if you in exam use elastic limit, you lose 1 mark already. It's wrong. Okay, Hooke's law extension is directly proportional to the force applied as long as never exceed limit of proportionality. Okay, not elastic limit. Okay, so please put in your mind. Okay, so elastic behavior, Hooke's law graph. If you put force versus extension, the straight line region, the tip of the straight line region, this point P is called limit of proportionality. This is called limit of proportionality. The one I told you now. Limit of proportionality. Okay. Sorry. Okay. Okay, so that's about Hooke's law. Okay. So now we're going to learn something new. Okay. Stress. Okay. Stress. Of course, you as a A-level students, now you got a lot of stress, human stress. But material also experience stress. Stress of the material can be measured. Okay. Greater the stress to the material means more chances for the material to damage. Stress. So in material science, the stress is defined as the tensile force act normally across a cross-section area. The stress is given by force over area is stress. Force per unit cross-sectional area. Of course, it looks like same as the pressure formula. It's a pressure formula. But here for material, we call it as stress. Force over area. Okay. Pressure and stress, not same. Pressure, what difference? Pressure is a scalar quantity, okay, but stress is a vector quantity. Stress we can break into components, horizontal component, vertical component, we can break stress, but pressure we can't break into components. So that's the main difference of pressure and stress, although they share the same formula, force over area. So let's say you have a wire, and you apply a force of F, okay, and the area is A. So the stress applied to the material is force over area, force per unit cross-sectional area. Okay, so that is stress. So the symbol is sigma, Greek sign. Okay, use a lot of Greek sign, sigma. Okay, so stress is Newton per meter squared, or another unit called Pascal. Okay, and force acting on an area of the plane, and A is the cross-sectional area of the plane. Stress. Okay. So how do you reduce stress to the material? How to make the stress is lower? If a material has a low stress, good for the structure, won't easily cracks. How do you bring a lower stress? That means you apply a low force or use a bigger cross-sectional area. Okay, bigger cross-sectional area. Then you can reduce the stress. Okay, big stress might damage the structure. Okay, so that is stress. Stress causes strain. Okay, this also like daily life, we can say a lot of strain. Stress causes strain, not strain causes stress. Stress causes strain. So material also experience strain due to stress. Okay, now we can measure strain also. What is strain? Strain is epsilon. This is called epsilon. Strain is, of course, no unit. Strain is extension over the original length. Is strain. This what? This is your extension over the what? Or over the original length. This is your strain. Original length. Original length. So when a stress act object the original length, the cost to it extend by a small x, the strain is given by x over L naught. The strain is no unit. It don't have unitless quantity. And the original length of the specimen L naught, and the x is the deformation of the original length. Okay. So let's say you have a wire. They say a force is applied until the strain is 1. Until the strain is 1. Let's say the original length is 1 meter. Force is applied until strain become 1. That means what is the new length of the material? What is the new length of the material after the force is applied? If strain is 1. Strain is 1 means what? Extension over the original length is 1. Original length is how much? 1 meter. That means the extension alone is how much? Extension alone. Extension alone is 1 meter. So the total length of the wire now is what? The original length 1 meter, and extension makes another 1 meter. So this is 2 meter now, 2 meter now. So if a wire can extend the exact length of the original length, we say strain is 1. Strain is 1. That means extension alone is like 1 times of the original length. Okay. They said there is some specific rubber. Can have strain of 8. Strain of 8 means what? If the rubber has a length of 1 meter means, if it has a strain of 8 means, what is the total length of the rubber will be? When I have a strain of 8, total length will be 9 meter, including the original length. Okay, that is strain. So, 2 quantities you learn. Stress is force over area, and strain is extension over the original length. Extension over the original length. Okay. Okay, one example. A force of 100 Newton acts on an area of 20 millimeter square. Calculate the stress. So what is the stress? Force over cross-sectional area. So you should get 1.5 times 10 power of 6 Pascal. I think this is an easy question. Just force divided by area. But area I have to change to meter square. So 100 Newton divided by what? 20 times, how much? 10 to the power of negative. Millimeter change to meter. -6, -6 because square one. -6 conversion, make sure it's correct to get this answer. Okay. So 1.5 100 divided by 20. Okay. So a bar length of 2.2 meters stretched a distance of 5 millimeter. Calculate the strain. What is the strain for the second one? So strain is extension over the original length. So of course 5 mm. So 5 times 10 power -3 change to meter divided by 2.2 give you the strain. Okay, so you should get 2.27 times 10 power of -3. No unit strain. Okay, then okay, now this question. 1 minute for you. Give a try. Okay, 1 minute for you. Please calculate the stress and strain for this material. 3. Stress is force per unit area. Strain is extension over the original length. But this is a pipe. This is a pipe with outer diameter is how much? 50 mm. 50 mm. And inner diameter. Oh, that means there is a cavity inside. There is a cavity, empty slot. Inner diameter is how much? Inner diameter is 40 mm. 40 mm. So the area you must calculate, the area you must use is only the area which has the material. Only this area you have to use. So stress is what? Force over area. Force is 100 kilonewton. So 100 times 10 power of 3. Okay. Which area do you use? The area where the material lies. That means you must use what? Pi r squared, the diameter, big one, the big one. So big diameter is how much? 25. Pi r 25. 25 times 10 power of -3, right? Square minus pi 2, right? 40 mm is 20. So 20 times 10 power of -3 square will give you the stress. The stress, you must use the side areas. What do you got? Where the pipe is maybe not. So do you get these answers? 1.41 times 10 power of 8 should be your stress. Remember, you only can take the area at the side. Area at the side. Pi r squared of the big diameter minus pi r squared of the small diameter will give you the area of the side. That's what you need to use. So force divided by that area of the side will give you, should give you 1.41 times 10 power of 8 Pascal. Okay, unit for stress is Pascal. Okay. Okay, then how do you find strain? Strain is sigma. Strain is what? Extension over the original length. So extension is how much? Shortened by 1 mm. So that means extension, this is a compression line, 1 mm. And the original length is how much? This is the original length is 1 meter. Yeah. So it's 1 times 10 power -3 is the strain, the compressive strain. Okay. So any questions so far? Okay. So yeah, so this is today's lesson. Okay. So today's lesson, what you learn is you learn about Hooke's law. You learn about spring connected in series parallel. Then introducing to a new term, two-term called stress and strain. Okay. What is stress? Stress is force per unit cross-sectional area of a material. Strain is extension of the ratio of extension to the original length. Okay. Stress causes strain. Unit for stress is what? Pascal. Unit for strain is what? Unitless. Okay. Big stress going to yield a big strain. Okay. Stress, is it good or bad for a material? It's bad. Okay. It's bad for a material. So engineer, when they build like a bridge, okay, they need to use the pillar to a certain cross-sectional area so that it can withstand a great certain stress. Okay. So there is a minimum cross-sectional area is required. Okay, let's say the cross-sectional area of the pillar required, let's say it's about 20 centimeter. So they might go use a pillar of maybe 21 or 22 centimeter. They can't go like 30 centimeter because costly again. Yeah. So stress is damaging for the structure. We need to reduce the stress by using a bigger cross-sectional area. Of course, it costs economically not good. Okay. Any questions so far today's lesson? No questions, Okay, class. We will be continuing this topic next class. Next class going to be, we talk about something called Young modulus. You read through first. Yeah, read through first. Then we try to finish another 2 or 3 classes of this topic. Okay. The 2 questions your friend gives you, maybe I answer him later, or we discuss the next class. Any questions? No questions, Okay. I hope at the background you are doing the past years. Okay, keep it up. I see you tomorrow. Tomorrow at 3:30, right? Okay. So if you don't have questions, we can stop here. Any questions? No questions, Okay then, class. See you tomorrow, 3:30.